There have been 5 moments in the history of life when the system we call Earth approached a limit, when the balance between environment and biology broke down on a global scale. 2 of them are widely known. The event that ended the non-avian dinosaurs, the Cretaceous-Paleogene extinction event, triggered by an impact that reshaped the climate in a matter of years. And earlier still, the Permian-Triassic extinction event, when volcanic activity and atmospheric change removed an estimated 90% of marine species. But the first of these events, the one that established the pattern, receives far less attention. It took place approximately 443 million years ago, at the boundary between the Ordovician and Silurian periods. And it did not unfold as a single catastrophe. It came in 2 distinct phases, separated by time, driven by different mechanisms, and affecting different parts of the global system. The first reshaped climate and sea level. The second altered the chemistry of the oceans themselves. This distinction matters. It suggests that large-scale extinctions don't always come from a single shock, but from a chain of changes that gradually destabilize the system. To understand how that happens, we need to begin before the collapse, with the world that existed when the system was still intact. To understand what was lost, we have to begin with what came before. In the Cambrian period, beginning roughly 541 million years ago, life underwent a transformation, often described as the Cambrian explosion. Within a relatively short span of geological time, on the order of 20 to 25 million years, most of the fundamental body plans that define animal life today first appeared. Arthropods with segmented exoskeletons, early mollusks, echinoderms, and primitive chordates all emerge in the fossil record during this interval. These were not incremental changes. They were structural solutions to fundamental biological problems: movement, feeding, sensing, and protection. Yet despite this remarkable anatomical innovation, the Cambrian world remained ecologically limited. Most ecosystems were concentrated on or near the seafloor, particularly along continental margins. Primary production was dominated by simple algae and cyanobacteria, supporting short food chains, often just 2 or 3 steps from producers to top consumers. Fossil and trace evidence shows that predation was already shaping evolution, driving shells, spines, and burrowing, but predator-prey networks remained limited in scale and stability. Large mobile predators existed, but they were relatively rare, and their ecosystems lacked the deep redundancy and buffering capacity seen in later periods. This is the key distinction. The Cambrian built the parts of complex life, but not yet a fully integrated ecosystem. Diversity was rising, but interactions remained shallow. That transition begins in the Ordovician period, starting around 485 million years ago. During this period, a major evolutionary expansion, known as the Great Ordovician Biodiversification Event, reshaped marine life. Fossil data indicate that the number of marine genera increased by approximately 3-fold, with particularly strong diversification among brachiopods, bryozoans, mollusks, and echinoderms. More importantly, this diversification was structured. Organisms began to occupy more specialized ecological roles. Suspension feeders formed dense communities that filtered large volumes of seawater. Reef-like structures built by early corals and bryozoans introduced physical complexity into marine habitats. Mobile organisms expanded into the water column, while benthic communities became more stratified, with organisms living both on and within sediments. At the same time, food webs lengthened. The rise of larger, more active predators like early cephalopods suggests enough energy was flowing through the system to support higher trophic levels. This implies not only increased primary productivity, but also more efficient transfer of energy between levels. For the first time, Earth's oceans supported ecosystems that were not just diverse, but organized systems defined by stable interactions, layered energy flow, and interdependent roles. By the early to middle Ordovician period, the transformation becomes measurable. In the fossil record, the number of marine animal genera increases by roughly a factor of 3 over a span of about 25 to 30 million years. This interval is known as the Great Ordovician Biodiversification Event. But the significance of this event is not simply numerical, it is structural. What is changing is not just how many organisms exist, but how they are organized within the system. At the base of this emerging structure are the filter feeders. Groups such as brachiopods and bryozoans expand rapidly, forming dense, persistent communities across shallow marine environments. These organisms extract microscopic food particles, phytoplankton, and organic detritus from the water column, effectively converting diffuse energy into concentrated biomass. In doing so, they stabilize the lower levels of the food web. Their abundance is not incidental. It reflects an increase in primary productivity in the oceans, likely driven by nutrient input from weathering and ocean circulation. Above this biological foundation, physical structure begins to appear. Reef systems constructed by early corals, bryozoans, and other calcifying organisms introduce three-dimensional complexity into marine habitats. These are not reefs in the modern sense, but they serve a similar function. They create surfaces, cavities, and gradients of light and flow, allowing multiple species to coexist in close proximity. This spatial complexity increases local diversity and creates new ecological opportunities. Within and around these environments, mobility becomes more important. Trilobites, already established in the Cambrian, undergo significant diversification during the Ordovician. Different species adapt to different modes of life. Some remain benthic scavengers. Others become active burrowers, and some evolve into swimmers, capable of moving through the water column. Their variation reflects a broader trend, the partitioning of ecological space into more specialized roles. At the upper levels of the system, a new kind of predator emerges. Cephalopods, particularly early nautiloids, increase in size and ecological importance. Some develop long, straight shells and reach lengths of several feet. These animals are capable of active movement using jet propulsion, and their presence indicates something critical. The system now supports sustained predation at higher trophic levels. Large predators do not exist in isolation. Their survival depends on a continuous and reliable flow of energy from the base of the food web upward. To support even a single apex predator requires a wide and productive base of primary producers, intermediate consumers, and multiple pathways of energy transfer. The appearance of these predators is therefore not just a biological milestone. It is a system-level signal. What we see in the Ordovician is the emergence of a layered, interconnected network. Energy enters through photosynthesis, is processed by filter feeders and grazers, transferred through multiple consumer levels, and ultimately concentrated in mobile predators. At each stage, organisms are not acting independently. They are linked through feeding relationships, competition, and shared environments. This is the essential shift. Life is no longer just diversifying. It is becoming organized into a system in which each component depends on the stability and function of the others. By the middle of the Ordovician period, the expansion of life is no longer just a biological story. It is a planetary one. The structure we see emerging in the oceans is supported quietly but decisively by the physical configuration of the Earth itself. The continents are arranged in a way with no modern equivalent. Gondwana dominates the southern hemisphere, while smaller landmasses, Laurentia, Baltica, and Avalonia, lie closer to the equator. This configuration matters not for its geography alone, but for what it allows the oceans to become. Sea levels during much of the Ordovician were high, flooding continental interiors and creating vast, shallow seas across thousands of miles. These broad, sunlit waters were not marginal. They were the central engine of the system. In these shallow waters, sunlight penetrates easily to the sea floor, enabling widespread photosynthesis by marine algae and cyanobacteria. At the same time, chemical weathering of continental rocks delivers a steady supply of nutrients, phosphorus, iron, and other dissolved ions into the oceans. The result is a combination that is both simple and powerful: light, nutrients, and space. Atmospheric carbon dioxide levels during this period are significantly higher than today, with estimates ranging from 8 to 15 times pre-industrial concentrations. This elevated CO2 drives a greenhouse climate. Global temperatures are warmer, seasonal extremes are reduced, and crucially, there are no permanent polar ice caps in the early and middle Ordovician. Without large ice sheets to lock away water, sea levels remain high and stable over long intervals. This stability allows ecosystems to persist and expand. It reduces environmental volatility and enables the continuous accumulation of biological complexity. Energy enters the system through photosynthesis and moves upward through increasingly elaborate food webs with relatively little interruption. And that continuity is essential. Large active predators such as the cephalopods emerging at the top of the Ordovician food web require not just abundance, but reliability. They depend on a system that produces energy not in bursts, but as a sustained flow. This is what the Ordovician world provides. The shallow seas act as vast biological processors, converting solar energy into biomass at a scale that had not previously existed. That energy moves step by step through the ecosystem, supporting organisms of increasing size, mobility, and specialization. What emerges is not just a diverse biosphere, but an efficient one, where production, consumption, and recycling are tightly linked, and energy moves with minimal loss. This is the condition at its peak. A global ecosystem operating at high capacity, supported by a climate and geography that for a time makes such efficiency possible. By the height of the Ordovician period, the system appears stable, productive, diverse, and expansive. But that stability is conditional. It depends on a narrow set of environmental parameters held within a specific range over long periods of time. Two of those conditions are fundamental: high sea levels and a consistently warm climate. The shallow continental seas that support most biological activity exist only as long as global sea level remains elevated. A significant drop would expose vast areas of seafloor, removing the very habitats on which these ecosystems depend. In the same way, temperature stability maintains the chemical and physical structure of the oceans. Even gradual shifts can alter circulation patterns, nutrient distribution, and the balance between different forms of marine life. Beneath the surface, another constraint is already in place. The Ordovician Ocean is not fully mixed in the way modern oceans are. Without strong polar cooling to drive deep water formation, circulation is weaker, and the water column becomes stratified. Warm, oxygen-rich surface waters remain separated from deeper layers. As a result, large portions of the deep ocean are relatively low in oxygen, in some regions approaching anoxic conditions. This matters because it limits where complex life can exist. Many benthic communities are confined to well-oxygenated shallow zones, while deeper environments remain biologically restricted. The system is productive but unevenly so, with much of its complexity concentrated in a relatively thin surface layer. At the same time, changes are beginning on land. Primitive plants, likely small, non-vascular forms similar to modern bryophytes, are starting to colonize moist terrestrial surfaces. Their impact is subtle but measurable. Through photosynthesis, they draw down atmospheric carbon dioxide. Through their root-like structures, they enhance the chemical weathering of silicate rocks, a process that further removes CO2 from the atmosphere and transports dissolved ions into the ocean. Individually, these processes are slow, but over millions of years, they alter the balance of the carbon cycle. This is the underlying pattern. As the system becomes more complex, it also becomes more dependent on climate stability, on sea level, on ocean chemistry. Its strength lies in its connectivity, but that same connectivity introduces sensitivity. By around 460 million years ago, during the middle of the Ordovician period, the first indications of change began to appear, not in the organisms themselves, but in the chemical record they leave behind. Marine sediments from this interval preserve a shift in the ratio of carbon isotopes, specifically between carbon-12 and carbon-13. This signal, known as a carbon isotope excursion, reflects a disturbance in the global carbon cycle. Under stable conditions, the balance between carbon entering the system through volcanic outgassing and weathering and carbon being removed, primarily through the burial of organic matter, remains relatively constant. When that balance shifts, it suggests that the system is no longer in equilibrium. Several mechanisms could account for this change. Increased volcanic activity associated with tectonic processes active during the Ordovician may have released large quantities of carbon dioxide into the atmosphere. At the same time, enhanced chemical weathering of continental rocks, possibly accelerated by the early spread of land plants, could have drawn carbon dioxide out of the atmosphere more efficiently. These processes do not act in isolation. They interact, sometimes reinforcing, sometimes counteracting one another. There are also more speculative possibilities. One hypothesis proposes that a nearby gamma-ray burst may have altered atmospheric chemistry, affecting ozone levels and surface radiation. The evidence for this remains limited and debated, and it is not required to explain the broader pattern. What matters is the direction of change. The carbon cycle, which underpins long-term climate stability, is beginning to shift. The system has not yet collapsed, but it is no longer operating within the same stable bounds that supported its earlier expansion. By the late Ordovician period, the trajectory of the system began to shift in a way that was quiet at first, but decisive in outcome. The first phase of the extinction is not triggered by a sudden external shock. It emerges from the planet's own dynamics, long-term climate shifts driven by plate tectonics. The supercontinent Gondwana continues its gradual movement toward the South Pole. This motion is slow on human timescales, but over millions of years it alters the distribution of solar energy across the planet. As large landmasses enter polar latitudes, they provide a stable surface on which snow and ice can accumulate. Unlike ocean water, which circulates and redistributes heat, continental interiors can retain cold conditions long enough for ice sheets to expand. As glaciation begins, it initiates reinforcing feedback. Ice reflects incoming solar radiation more efficiently than rock or water, reducing the amount of heat absorbed at the surface. This cooling encourages further ice growth, strengthening what is known as the ice albedo feedback. Over time, this process amplifies what may have begun as a relatively modest climatic shift into a sustained period of global cooling. Geological evidence of this shift appears in glacial deposits across what was once southern Gondwana, now parts of North Africa and South America. These deposits indicate the presence of extensive ice sheets during the Hernantian stage, marking one of the most significant glaciations of the early Paleozoic. The most immediate biological consequence is not the drop in temperature itself, but the associated fall in sea level. As water is locked into expanding ice sheets, global sea level declines likely by tens of feet, and possibly more. This exposes large portions of the shallow continental shelves, the very environments that had supported the highest levels of biodiversity and productivity throughout the Ordovician. These shallow seas were the operational core of the system. They concentrated sunlight, nutrients, and biological activity into highly efficient networks. When they disappear, the structure of the ecosystem is not simply stressed, it is physically reduced. Habitats contract, populations fragment, and the connections between different parts of the food web begin to break down. This is the defining mechanism of the first extinction pulse. Life is not eliminated by a direct destructive force. Instead, the environmental framework that sustains it is progressively removed. The system does not collapse because its components fail in isolation. It collapses because the conditions that allowed those components to function consistently and at scale can no longer be maintained. In the aftermath of the first extinction pulse, the system did not disappear. It contracts fragments and then gradually begins to reorganize. By the latest Ordovician period, as glacial conditions stabilize and sea level begins to fluctuate, some marine environments persist. Not all shallow habitats are lost, and in the refuges that remain along continental margins and in isolated basins, surviving lineages continue to function. The fossil record shows that extinction during this interval is selective rather than absolute. Certain brachiopods, trilobites, and other marine groups persist, but often with reduced diversity and narrower ecological roles. Communities that had once been broad and complex are replaced by assemblages composed of fewer species, occupying fewer niches. This is not a restoration of what existed before. It is a reconfiguration under constraint. Food webs shorten. Energy pathways lose redundancy. The structure remains: producers, consumers, predators, but with fewer connections, it becomes more vulnerable. In ecological terms, resilience declines. A disturbance that might previously have been absorbed can now propagate more easily through the system. There are also signs of opportunism. Some surviving species expand into ecological spaces left vacant by extinction, temporarily increasing their abundance. But this expansion does not indicate long-term stability. It reflects the absence of competition rather than the presence of a fully functioning system. What emerges during this interval is a biosphere that is still active but diminished. It continues to operate, but with reduced complexity and reduced buffering capacity. This is the critical point. Recovery in this context does not mean a return to the previous state. It represents a transitional phase, a system reorganizing under altered conditions, still adjusting, still incomplete. And because of that, it remains exposed. As the glacial phase begins to recede, the system shifts once again, but not toward recovery. The second phase of the extinction emerges from the consequences of the first. When the ice sheets over Gondwana begin to melt, water returns to the oceans. Global sea levels rise, flooding continental margins and re-expanding shallow marine environments. At first, this might appear to restore the conditions that had supported Ordovician life, but the underlying structure of the ocean has changed. Warming temperatures reduce the density contrast between surface and deep waters, and circulation weakens. The ocean becomes more strongly stratified, with limited mixing between oxygen-rich surface layers and deeper zones. At the same time, the influx of nutrients released through weathering during the glacial interval can stimulate high levels of surface productivity. When this organic material sinks and decomposes, it consumes dissolved oxygen. The result is the expansion of low oxygen and, in some regions, anoxic conditions across large areas of the seafloor. These environments are inhospitable to most complex marine organisms, particularly those already weakened by the earlier loss of habitat. The fossil record indicates that many of the species that survived the initial glaciation declined during this interval. Extinction continues, not as a sudden pulse, but as a sustained reduction in viable habitat and environmental stability. This is the critical insight. The second extinction is not an independent event. It is a continuation driven by the altered state of the system after the first disruption. The initial cooling removed the structure. The subsequent warming removes the stability needed to rebuild it. What we have seen is not a single catastrophe, but a sequence. Two disruptions acting on two different vulnerabilities within the same system. First, temperature global cooling that removed the shallow seas on which most life depended. Then, chemistry declining oxygen levels as the oceans reorganized, limiting where life could persist. This is the significance of the Ordovician-Silurian extinction event. It is the first clear example of how a complex ecosystem collapses not instantly, but in stages. Each phase reduces stability until recovery is no longer possible. If you find this kind of deep time perspective valuable, subscribe to support more work like this.